Hello, my name is Ali Mukhtari from University of Louisiana at Lafayette, and today I want to talk about autonomous task dropping mechanism to achieve robustness in heterogeneous computing systems. The performance of a heterogeneous computing systems is perturbed by uncertainty in both task execution time and arrival rate. When you have different tasks running on heterogeneous computing systems, you cannot predict the exact value of execution time. So it can be said that this parameter is uncertain, and arrival rate of tasks is also not known, and it's uncertain. Uncertainty in arrival rate may lead to oversubscription situation, that is an overloaded system that cannot complete all tasks by their deadline. Co-occurrence of both task arrival and execution uncertainties in a heterogeneous system leads to poor resource allocation decision and lack of robustness. This is particularly crucial when resources are not abundant, like in edge computing, or the resources cannot be acquired due to budget constraint in cloud environments. So what is robustness? Robustness is defined as the ability to maintain systems performance in face of uncertainties. To quantify the robustness, we use these metrics: number of tasks completed on time within a given period of time. So what's the challenging problem? The problem is how to make HC system robust against uncertainties in task execution time and arrival rate. And next slides, I will explain our solution. First, to capture the uncertainty in execution time, we model the execution time using statistical distribution. Then the model is used to calculate the probability of on-time completion for each task. Next, we propose a task dropping mechanism proactively drops tasks with low chance of success. Dropping an unlikely to succeed task reduces the incurred cost of using resources. Moreover, it increases the chance of success for the remaining tasks. Dropping improves the chance of success for the tasks behind the drop tasks, as they can begin their execution earlier. However, we miss the chance of success of completing a task, hence it reduces the robustness. To attain the maximum robustness, a trade-off should be considered for any dropping decision. We propose a mathematical model that at any mapping event determines the optimal task dropping decision so that the overall system robustness is maximized. So our contributions are listed as follows: developing a mathematical model for optimal proactive task dropping in a HC system, proposing an autonomous proactive task dropping heuristic in HC system, and finally analyzing the impact of task dropping mechanism and robustness of both heterogeneous and homogeneous systems under varying workload characteristics. This research is motivated by a HC system used for transcoding live video streaming tasks. In this system, each task has an individual deadline and it has to complete before the deadline. There is no value for executing tasks miss their deadline. We consider the execution time of each task type and each mission type as a discrete random variable. Then it is modeled by its probability mass function. Eij of t representing the probability that task type I and mission type j takes t time units to execute. And execution time distribution can be learned from the historic execution time information. So here the criteria for proactive task dropping is mentioned. The task should be dropped if it increases the likelihood of having more tasks completed on time, or in other words, if it increases the system robustness. Along with proactive task dropping, we have another dropping mechanism called reactive task dropping. This mechanism drops a pending task missed its deadline. It's called reactive task dropping since it works in reaction to missing a task's deadline. Prior to find the probability of on-time task completion, we need to calculate its completion time distribution. It can be easily done by convolving its execution time distribution with the completion time distribution of the task ahead of it, task I minus 1. Here we can see the mathematical formulation for it. First, for time impulses in completion time less than the task deadline, we need to convolve the completion time of task I minus 1 with the execution time of task I for all impulses less than delta I. For t greater than delta I, the first term is as the same as the t less than delta I. The only difference is that we consider delta I as time limit in summation. But if task I minus 1 completed at time which is greater than the deadline of task I will be discarded and its execution time is considered 0. So in convolutional formulation, it is equivalent to simply add the impulses of completion time of task I minus 1 for t greater than delta I to the first term. Once we have completion time of a task in hand, we can easily determine the chance of success for a task. The chance of success for the task is the probability of on-time completion of that task. So it can be determined by summing the probabilities in completion time that are less than the deadlines. Here I will explain how to calculate the chance of success for a task by giving an example. We have the execution time of task I, completion time of task I minus 1, and we want to find the completion time distribution of task I. First, we need to exclude the impulses of completion time of task I minus 1 that is greater than the deadline of task I, this portion. Next, we need to convolve the execution time distribution with the resulted distribution from step 1, the excluded completion time of task I minus 1. For example, to find the completion time of task I at 11, we need to multiply these two probabilities of completing task I minus 1 at 10 and executing task I in 1 time unit, which would be 0.36. Or for finding the completion time at 12 for task I, we have two situations. We may have completion time 11 and execution time 1, or we may have completion time 10 and execution time 2. For the first one, for example, for the first one, completion time of 11 and execution time of 1, we may have 18% chance. And for the second one, we may have 24% chance. And finally, together, we can have 42% chance. And the same way for 13 and 14. The final step is to add the excluded part of the completion time distribution of task I minus 1 to the resulted distribution from step 2. This is the excluded part, 5% chance of completing task I minus 1 at 13, which is greater than the delta I. At this time, the execution time is 0, so we simply add this 5% chance to the resulted distribution that we had in step 2. So now we have 20% chance of completing task I on time 13. And by adding these two probabilities, 11 and 12, which is less than the deadline of task I, we may have the chance of success for task I, which would be 78%. So we define instantaneous robustness as the sum of the chance of success for all tasks in mission queue, and we hypothesized that the overall system robustness is likely to be improved only if instantaneous robustness is improved at each individual mapping event. The task in a mission queue divide the mission queue in two zones, influence zone and dependence zone. Completion time of task I not only depend on its execution time, but also on the completion time of the tasks ahead of it. So it is said that tasks ahead of task I in mission queue are in dependence zone of task I. In the same way, task I influences the completion time of tasks behind it in the mission queue. So it is said that these tasks are in influence zone of task I. So we can say that dropping tasks would be appropriate decision only if it improves the instantaneous robustness of tasks in the influence zone. The optimal proactive task dropping mechanism investigate all subsets of tasks in mission queue to find a subset of tasks whose dropping maximizes their instantaneous robustness. This approach will examine all subsets to find the best one as opposed to deciding for each task in isolation. Examining all subsets of tasks in optimal approach is costly. To address this problem, we propose proactive task dropping heuristics. This heuristics is a suboptimal solution within a feasible time. It does not examine all subsets. Instead, it operates on a task-by-task basis. In this heuristics, a task is dropped if instantaneous robustness when it is provisionally dropped is sufficiently greater than when the task is not dropped. We consider robustness improvement factor beta to control the desired difference between Rj when I is provisionally dropped and when it's not dropped. In addition, we limit the number of tasks in influence zone of task I that are investigated for robustness improvement. The number of tasks located immediately after task I in its influence zone that we want to investigate in proactive task dropping heuristics called effective depth. The robustness improvement is only examined for the tasks in eta range of effective depths and influence zone of task I. Here you can see the algorithm of proactive task dropping heuristics. In line 2, tasks miss their deadline are reactively dropped. Then lines 4 to 7 for each task I in mission queue find the instantaneous robustness if task I provisionally dropped and not dropped. And finally at line 8, the mechanism decides to drop a task or not. The next slides show some experimental results. First, in the first experiment, we analyzed how the robustness of a system differs by varying the values of effective depth. The horizontal axis shows different values of effective depth, and the vertical axis shows the system robustness in form of percentage of tasks completed on time. Here you can see that there is no significant difference in robustness for effective depth greater than 2. It is because of the fact that in our subscribed system, the impact of dropping task I fades out quickly within the first couple of tasks in the influence zone of task I. In the next experiment, we varied the value of beta in the range of 1 to 4, and for each configuration, we measured the system robustness. The trend of graphs shows that by increasing the beta value, proactive task dropping heuristics becomes more conservative and is less engaged in the task dropping operation. At the end of the spectrum, very large value for beta neutralizes the impact of proactive task dropping heuristics. To examine both the generality of the dropping mechanism and its impact on the system robustness in this experiment, we applied the proactive task dropping heuristics on widely used mapping heuristics. Then, for each mapping heuristics, we measured the system robustness with proactive task dropping and without proactive task dropping heuristics involved. Results showed that when proactive task dropping is in place, all three mapping heuristics provide almost the same robustness. It's because of the fact that proactive task dropping prunes tasks whose chance of success is low. In addition, we can conclude that if we put a reasonable dropping mechanism in place, we do not have to deploy a complex mapping heuristics. In the next experiment, our goal is to evaluate how proactive dropping can enhance the system robustness against compound uncertainty in both task execution times and arrival. We picked PAM as the mapping heuristics for this study. The experiment results demonstrate that as the systems becomes more oversubscribed, the system robustness declines. Further analysis between PAM optimal and PAM heuristic revealed that, regardless of oversubscription level, there is no significant difference between these two approaches. While the focus of this paper is to maximize the system robustness in HC system, there are other metrics of success to consider. One of these is cost. The goal of this experiment is to analyze the impact of proactive task dropping heuristics on the incurred cost of using such resources. For that purpose, pricing from Amazon Cloud was mapped to the simulation machines. To create a normalized view of the incurred costs, the price incurred to process the task is divided by the percentage of tasks completed on time. Results show that in an oversubscribed system, both PAM threshold and PAM heuristics incur significantly, about 50%, lower cost per completed task than MM, mean completion. The reason for the improvement in PAM heuristic is prioritizing tasks that are most likely to succeed. And finally, to wrap it up, we investigated robustness of HC system against the compound uncertainty, result from uncertain task execution time and uncertain task arrivals. Also, to attain the robustness goal, we proposed an autonomous dropping mechanism that captures the compound uncertainty and proactively drop tasks whose chance of success is low. The proposed proactive task dropping mechanism provides the following advantages. First, it's dynamic and does not require user intervention like PAM threshold. And architecturally, it's less complicated and can cooperate with any mapping heuristics in a resource allocation system. And also it provides a higher system robustness. For the future work, we plan to extend the probabilistic analysis to consider approximately computing tasks in addition to task dropping. And also, we plan to extend the probabilistic analysis and cover other types of compound uncertainties like network latency or resource failures. Here you can see our contact information. Please feel free to ask questions and let us know if you have any question about our research work. Thank you very much.